So for people who attend us online, please mute your microphones because it must be done. And the first presentation is by Kaj Riska, professor from Aalto University and also NTNU in Trondheim. The presentation will be in two parts. One is kind of overview what we know today and what we did know 5 years ago when we had that 4 months program. And second part, it will be research presentation, new research done by Kaj. Please.
Thank you, Professor Korobkin. Well, the affiliations for me, I mean, they are a bit old because I resigned from Aalto University 15 years ago and I actually retired from NTNU a couple of years ago. So both are a little bit sort of old. They are valid in a way, of course, but now that's why I didn't put any affiliation there. So I'm retired, following a bit of science and doing bits and pieces. As Professor Korobkin mentioned, actually the organizers presented me with 2 questions. And well, I actually modified them into 4. And the idea actually is to describe a little bit what is marine ice engineering, because it was mentioned that the ice engineering is more the topic of this week. So I guess this is an introduction for that. And also the questions, the first question here relates a little bit to ice engineering. I come back to that. I actually agree with the first change there, not really that much with the second change. And the trend in the question I will also discuss a little bit. Anyway, needs from scientific research is something I also describe here. I try to be brief because I actually wanted to describe really the pressure area things more than this kind of a bit bureaucratic things, but let's bear with me. Anyway, this is the basic case of most of the marine ice engineering. Ship or an offshore structure hitting ice and different types of ice. This is icebreaker Helene hitting this multi-year ice in Baffin Bay during the trial or inaugurational cruise, because she left New Orleans and the test in Baffin Bay and then traversed Northwest Passage to Seattle. And I was with her in the first part of the voyage. Anyway, if you split then this case into sub-factors, this is what you end up. You have a structure, you have ice coming in and which is failing, and then it's pushed down quite quickly. There's transient hydrodynamics in play, which hasn't been tackled, by the way. Well, I know one doctoral dissertation in Delft University which has tackled this, but only one. Added mass won't do, because added mass is frequency dependent, and this is impulsive motion. This happens in 0.1 seconds or something, so it contains all the frequencies. Anyway, then there's dynamic bending of the ice and then rigid body motions. Local failure we have to somehow assess, and that is actually the subject area of my talk later on. And then there is ice-ice contact. This type of ice-ice contact usually leads to rafting and ridging. So rafting and ridging are something we have to also model in ice engineering. That's very important. Comes very often rafting, not really rafting, but ridging, and the forces related to ridging. When do the ridges form? And all these cases actually in offshore engineering and marine engineering are just dependent on these 3 main parameters: the inclination angle from vertical to inclined, ice thickness, and the relative speed. We should speak about relative speed. Participants are seeing my application. Well, that's good. Anyway, then I tried to list the topics, and this is of course very incomplete list, but just to give you an idea of what we are tackling and again I should have added marine ice engineering. I'm not onshore person really, so it's offshore. Well, the two first are by far the biggest topics. One is the ice force on ships and structures, or ice action as it is nowadays called. And then there is resistance to motion forward, well, astern of course also, and turning. That is a second topic which is recurring very often. And I actually noted here that what are physical, and there are some economical and operational questions coming back to them. Then of course there's ice cover. These are a little bit sort of more in details. Ice cover bearing capacity is important, add freeze and abrasion of port structures, that is very important also. Ice encroachment on or to bottom founded structures, ice is getting on. I'll show a couple of photos about that. Then icing is a question in ice engineering. Icing usually is, by the way, a nuisance. It's not really a hazard. It's a hazard only for very small ships, like fishing vessels and all that, because of the stability problems. Icing is occurring on an area, and stability is a question of volume. That is why it is only for smaller ships. Bigger ships, it's a nuisance. You have to warm radar scanners and stairs and all that to avoid ice, but that is just practical thing. Anyway, then I have ice growth models here, which might surprise you that is this engineering problem. It is an engineering problem by default in a way, that because it is for all predictions, ice thickness is the most important parameter from ice, by far the most. And it is very difficult to get. You get coverage and you get all that from satellites, ice thickness, very difficult to get. So, and scientists haven't been able to tell us this ice thickness. So we have been forced to start studying, engineers, I mean, studying the ice growth and growth of also deformed ice, not just level ice, but deformed ice. I mean, how it consolidates, that's the word used for that more. And we have been quite successful. We have had a couple of, well, I personally have had a couple of doctoral students doing that, where we have had problems. And I think that's the climate change thing, is the modeling the melt, when ice does disappear. I mentioned last week that ice is melting, well, top and bottom, yes, but also in the grain boundaries. So it's sort of a mechanical, thermomechanical or mechanothermal process, actually, ice growth. And that's quite difficult to get the precise date. In the beginning, it goes thinner, but then when it disappears, is still very empirical. Then I also added ice-induced vibrations. Ice is hitting structures and structures start to vibrate. There has been near disasters, incidents. There has been a couple of disasters in Bohai Bay in China because of ice-induced vibrations. Not really directly, but indirectly that way, that the jacket structure started vibrating, and that caused a gas leak and leading to an explosion. So the reason was the ice-induced vibration, but not perhaps you could say direct reason. Anyway, then we have a big area of fleet studies and oil field, gas field development. That's actually which are most interesting for us. The question is, of course, economical. For fleet study, the question is that if you have a Citronen mine in the northern Greenland, and you have ore and it's zinc, lead, copper. Well, they haven't developed it yet, but anyway, it's under planning. But anyway, the question is that they want to produce this and this many million tons per annum. How many ships do we need? That's a fleet study. So you have to model the ships going somewhere to Rotterdam or ARA, as it is called, Antwerp, Rotterdam, Amsterdam area. And then you have to, of course, decide the ship size and all that. But that is a fleet study, and it's quite important for Yamal LNG. Well, perhaps I shouldn't speak about Russian project, but Yamal LNG, there the question was that how many LNG carriers they need, and they considered between 14 and 16 LNG carriers, and each cost sort of 300 million euros. So I mean, it was a big decision, of course. They set in between 15, actually. A bit of an engineering compromise, typical. Anyway, and those are economical. the starting point usually is the resistance and all that sort of, you start from there. Then there are, of course, operational questions, tactical, strategic navigation. And that is actually the question here also that can be applied to operational questions, ice navigation. I come back to that, but this is not, tactical navigation is not really a problem. I mean, if you're experienced mariner, captain, master of a ship, and you sailed in ice, only thing what you require usually is that give me satellite images. I can interpret and I can do my optimization. When I was working as a professor in university, we tried to force on Finnish icebreakers our predictions and all kinds of interpretations of ice. No. Well, okay, you can send them to the bridge, but just send the satellite images. So I come back to this question a bit more, what is there. Anyway, most engineering design calculations require modeling of ice failure. That is also typical, that you have to model ice failure in order to, because the instant when ice fails gives the highest load usually. So it's the ice failure which is important. Well, a couple of examples of ice engineering studies. This is Grigoriak trials in 79. We were there actually. One of the trials I ran actually. But anyway, that was in Beaufort Sea, and the question was the longitudinal strength of the ships when they ram heavy ice pieces. You see the freeboard is high, so that was quite heavy. It led to actually the Arctic class requirements, this work. This was done in 79, and the Arctic class requirements came in 90s. So it required 20 years, but still it had an application. Then another question, what is important, is ships in compressive ice. This is a ship which got stuck in ice, and as you see, the ice started to pile on board. And this was the result. Ship didn't sink eventually, just lost sort of half a meter of the beam, as you see here, sort of. And this is anyway a question. I want to call it compressive ice. Some people want to call it pressurized ice, but I don't like it because compression has a direction. So it's more compressive to me. And then some scientists call this converging ice field, of course. It's not clear what happens here actually for ships. So some ships get stuck here, and this is the worst incident. Some ships just have no problem, and it's not exactly clear the interaction between a ship and a converging ice field. Then there's ice encroachment. Here is where the ridging studies are important, because this is sort of a ridging process. This is a pile which has been disassembled by supply vessels partly. You see nicely where the ice has gone. And this is another ice encroachment example. These are from Caspian Sea, where it is a real problem. Caspian Sea datum, actually, the sea level is going down, or lake level. It's officially a lake, even though it's salt water. Anyway, the water level is going down, and nobody really knows why. Caspian Sea is an interesting sea. I'm digressing a bit, but it's an interesting sea because there are rivers leading to Caspian Sea, but no rivers going out. So it's an interesting piece of water. Anyway, here is ice encroachment also. This is from a beach in northern Finland. This is interesting thing, that is this an ice encroachment also. I didn't see this myself. It was through NCC, one of the US news channels. And then there was a question of icebergs. Very often people think that this is a risk and we have to do something in ice engineering studies with the icebergs. For ships, this is not a problem. I mean, the Titanic and all that people say, but that was stupidity. I mean, that if ships collide with this, I mean, can you imagine? I mean, is it real? So the small pieces are the most dangerous one for ships, actually, what you can't see among all the other ice. That's actually the worst. But of course, offshore structures can't really avoid these. If they are somewhere, they are somewhere, and then they just expect these. Terra Nova off Newfoundland, there was an iceberg floating towards it, and it came within, was it 50 meters or 100 meters, very, very close. And well, it didn't hit in the end. But Canadian government got so furious that they didn't follow the safety instructions to to getting out from the location that they have to suspend production. And there was, of course, lots of negotiations then to get it going again. They promised that will be better next time. All right, then I planned 15 minutes for this, so I'm almost on time. Design for marine technology, Arctic marine technology. Well, I said that design requires tackling on all pertaining factors. So when you do design, you can't say that this is something I don't know, so I leave it aside and I concentrate on things what I know. I mean, in science, you have that freedom that you have to analyze and then solve the problems one at a time. Well, in simulation, of course, you have to have everything in a simulation in place. But mostly science should actually do analysis. But engineering, I mean, design requires that we have to solve, even though sometimes we are very worried when we give answers, but usually the good designers have a consolation that who knows better. You ask yourself that who knows better. And when you can't have an answer to that, okay, then you're happier. Not perhaps happy, but happier anyway. Scales 1 centimeter to 10 meters, that's typical engineering scale, and 1.1 seconds to 100 seconds roughly. This is not to say that there are, of course, if you study cracks and if cracking is important, then of course the scale goes down and also down both ends sort of on this. And then also you might say that there's also high end, I mean, design is usually done to ultimate limit state, which is 100 years return period prediction. So that's 100 years. 100 years sort of already. So, but engineering studies usually this is the scale where you are. Statistical analysis is important. Now this is something, I mean, what I said that I'll mention something what we should get from science. I mean, because statistical analysis is important, you have to do statistical analysis to get to ULS, 100 years return period. So you have to do that. And it's important to realize that we have to distinguish between internal, I call this is actually, I have coined this, internal and external stochasticity statistics. Internal, by internal, I mean that even in constant ice conditions, what the structure sees is very statistical. This is actually half an hour measurement from one frame, very local structure on a ship, with constant speed, well, as constant as it can be, and with constant levelized thickness, as constant as it can be. And you see that there's lots of variation. So this is something you have to take into account. I think that the breaking, way ice is broken by ships it's a chaotic process. But chaos is a definite word, and I have not got anybody to really prove that it is chaotic. So I call it rather a variable process, that it is very variable. But then you have to take into account the external stochasticity, which is just that you have so many different ice conditions meeting you. You encounter in a lifetime so many ice conditions. So that is the external and the internal. Both you have to take into account in doing design. Then there's an effect of climate change. That has been debated a lot. And actually the present opinion in engineering is that if your statistics proves that there is some sort of effect of making the conditions more benign, less severe, what you should do? You should disregard that. That's actually, it's put in one of the standards also, that if you see a little bit that way, no, but then you enter up questions that how, if you should disregard that, so how should you disregard? Anyway, that leads to very awkward questions actually in doing design. And this is something what have to be taken into account. I think that we have heard lots of melt ponds and also lots of waves in ice questions, and this is a new thing compared to the last one. There were a couple of presentations about melt ponds and also waves in ice, but now there have been more. And I think that it's an effect of climate change. I have commissioned a couple of research projects to give us an answer that how should we take the climate change into account, if we want to take it into account. But it's bewildering that for example, this is the levelized thickness, maximum measured levelized thickness in Resolute Bay in Canada. And well, there's actually a bit of a trend going up. So, and we got all similar data from Russia, Russian Arctic, and the same thing. So levelized has not changed. Well, if you would like to say, you say that it goes up and a little bit down, okay, I give you that. But there's not a big effect there. And what is that? How should we then take that into account in design, if we would like to do design for climate change? In ice, there's no answers for that. There has been quite some studies related to the waves, actually, wave heights and how the wave spectra change and all that. They have not been incorporated in rules or standards yet, but they are a bit more advanced than us ice scientists, I would say. Then my last question is the innovation in Arctic marine technology. How do they come by? And I did a search for innovations in ship technology, Arctic ship technology for 150 years, last 150 years. And I came to a surprising conclusion that it is always the engineers who design, and they have the innovation. And scientists come later explaining why it works. So it's quite surprising it is that way. How the engineers came to this idea. For example, bow propellers. It came from the ferries in US, Philadelphia and somewhere. There were ferries with propellers both ends. And they realized by practice just that the bow propeller is very good in ice. Well, and the icebreakers, our first icebreaker, Finnish-built icebreaker, had a bow propeller. And now most of the icebreakers have bow propellers, except those who have azimuthing thrusters. Again, that's just a different innovation. But anyway, that is surprising. I think that because I have been on both sides of the table, in the university trying to sell my ideas, and in industry trying to get answers to my questions. And I think that it's a question of pushing or pulling. I mean, scientists are pushing their ideas. And then industry, we were pulling. We wanted to have answers to our questions. And I can say that pushing is far easier. Far easier. It's not that easy to get answers from scientists. It's like you're baking at home and you run out of yeast. And you run to the closest shop and ask, please give me yeast. No, we don't have yeast. But we have these nice olives in oil. We have this nice cheese. But no, that won't help my problem. That is often how scientists do. I mean, they want to answer the questions what they know. And we just also ask questions what we don't know in industry. And they very often don't meet. I haven't any solution for this, but that's just my experience having been both sides of the table. When I was working for Total, we commissioned several doctoral dissertations, and in the beginning the candidate listened to us. Yes, this is good. But then they started analyzing and speaking with their professors and all that, and they diverted in the end somewhere. And that was the difficulty. I don't know. Anyway, that's something to think about. All right, now I go to an engineering topic. I said that the structure-ice contact is important. It's actually important in almost all the ice engineering problems. And I try to describe pressure-area relationship, because this is commonly described by pressure-area relationship in most of the ship rules, and in all of the ship rules, and also most of the Arctic structure rules, so using the pressure area. And the pressure area relationship means that observations, and this is so-called Sanderson plot, which was the first plot where Sanderson, working for BP, he collected all the results. There are lots of different results, and he noticed that the indentation, he called it indentation pressure, varies with contact area. Sort of this kind of, and this is log scale, so there is some sort of an exponent. It's called area exponent describing this. This is very surprising when it came out. He says that from 10 to 100,000 square meters to very small areas, it persists. I have a little bit of difficulties understanding how can something persist in so many orders of magnitude, but that is what he presented. He was the first one to present it. As you will see, there were measurements far earlier than 88. First one, what I found, and I didn't do a big literature research. I know Bob Frederick very well, so that's why I put this. But that was, as you see, 75. And he made this kind of indentation tests, and he came with a area exponent of -0.4. That was something, and here are his results. This is log paper, and this is linear. So, but those were his results. Then there has been done a lot of ship measurements. You notice here there's MV Arctic. That was actually, we did also those measurements. Then there's Louis and Laurent, the Canadian icebreaker, and all show this kind of trend of pressure area. Here is an interesting plot also that that when ships hit ice, the contact area grows, and of course in rebound you might think that it is getting a bit smaller, but the pressure area relationship persists also in the process. Here are other ship measurements, and I mentioned the Gregoriak measurements 81. They are included anyway. The same trend. Somebody fitted a line here with an exponent -0.57. It's a bit haphazard what kind of line you want to fit here. Of course, it's going down, but what is the exponent is a bit under discussion. Here are the offshore measurements taken from Dan's paper and Dan Masterson. And again, you see that the exponents -0.4 to -0.7. They are different. I don't describe these different measurement campaigns, except this Hobson's Choice ice island. This was a big ice island north of Canadian archipelago, where they flew huge amount of equipment with a Hercules airplane and did this kind of, made a big trench. I think this was 5 meters deep, and then a huge hydraulic jack and measured pressures. Anyway, they got pressure area, and also in one test there was a pressure area thing. I come back to these results in a minute. Then we did, that was after I defended my doctoral dissertation, we did measurements, this kind of measurements. Sorry, this is old. This was beginning of 80s, the reports, and they were not in electronic format, so I took copies, and this is not that good. There's a hydraulic jack here, and then we have ice piece here. It's like this, and then we crush it either this kind of rectangular thing down, or we made this kind of monopoly house type. We called these monopoly house types and crushed it. And then we measured the pressures, and also we had a Lexan transparent plate and high-speed video camera to see what is happening in the contact. That is actually the important thing. I hope this works. Yeah, it works. I found this and I digitized. Now what you see is that it starts there, and there's crushed ice flowing down. This is going down, and you see a line here in the middle. Come on, it won't stop. I wanted it to stop actually. Well, it won't start again. Anyway, the thing was that the line was continuous, very sharp, and continuous. It looked continuous and very sharp. Then we wanted to repeat this on board a ship. We asked us a question that is it a fact also, this one, what we saw in the laboratory. We did this kind of window on a ship hull, icebreaker hull, and then we had our pressure measuring plate here. This is from inside, and we had high-speed photography through the window. So we could see what is happening in the thing. And this is the window, and well, this is a support. And you see, now it's just ice, crushed ice or something, and this is just whole, but then there's a line. And ice goes down and breaks, and ship is going several knots, several meters per second. So it repeats soon again, this kind of line there again. You see that it is a bit wider, but it also looks continuous, the line. This is, by the way, a binary code, 8 digits. So it's from 0 to all ones in 1 second, so we could really time what happens. This is now slowed down this video. Anyway, important things is that in sea ice it's a bit wider the line, but continuous. In laboratory ice in -6, it was very narrow and clear. And here are the results then from our measurements. We had 3 different pressure gauges and, well, pressure area again. Surprising thing to remember is that we measured the highest peak. This is actually in white is in full scale in laboratory, which was definitely warmer ice. It was actually an outlier, a maverick, because I also calculated I fitted to the peak values, I fitted an extreme value distribution and then predicted what should be the pressure following the extreme value distribution. It's actually far down here. So this peak was something one-off actually. But anyway, it occurred, so we had a very high pressure, close to 60 megapascals. A bit surprising that. Anyway, then people had done aspect ratio results. This is from Canadian National Research Council, again, Gary and Surom, and they have similar effect versus pressure aspect ratio, width versus height. And for ship purposes, people have rather would like to describe not the pressure, but actually the force divided. This is the pressure, but then line load is force divided by load height, because that is for design purposes better quantity. And here are different ship measurements, and as you see, they are normalized for this one frame spacing load length. And you see that they follow this kind of distribution quite nicely. These are, of course, fits. And here are some results from Polar Sea 1986 trials. These are individual hits, so there's average line load versus line load length. The highest average line load which has been measured is roughly 4 meganewtons per meter. That is to give you an idea that of the magnitude where we are going. So 4 meganewtons per meter, which is quite a lot actually. Well, to think what is the origin of the pressure area thing, I also got results. Well, that is our paper. Robert Bridges, myself, and Hopkins were the authors. Anyway, we did discrete element simulations on a vertical structure. This is to design Caspian Sea structures. And then we calculated the line load versus load width. So we cut from the face, we cut different widths and calculated the load. And it's there also, clear, the dependency. That's, for me, that's a little bit surprising, and I'll say why. I would understand the beginning part, but it is really quite nice and continuous line, so that's a bit surprising. Anyway, these plots and results raise 2 main questions, which ice engineers usually refuse to ask. That actually sort of put under the carpet, sort of in a way. One is that what is the area used? What is the area? It is some clearly defined area, but usually it is the gauge area. I mean, you use certain gauges and you have an area, and then you have an area. You use that area, and you measure force actually. Most of the pressure measurements measure force. Only so-called tactile sensors and PVDF, polyvinyl difluoride film, react to pressure. And even tactile sensors, is it force or pressure? It's not clear. But anyway, you measure force and then you have a gauge area. In some cases, engineering cases, you have a clear area. Imagine that you have level ice and a pile or hitting. So then you have a clear area, clearly defined area. So in that case, you measure the force and you have a clear area. So there are cases, but in ship cases, the area is not at all clear. Ship is hitting ice and ice is crushed, and what is the area? It's not clear at all. The second question is, what is the pressure? You question both sides. What is the pressure? And how it is determined, measured? Well, it is measured by measuring force and dividing by the area you know. But is it an average over an area? Is it a maximum? It's not clear. Usually people, when they do the plot, they assume that it is an average over the area. That is the usual assumption, but it's not that clear. Well, area considerations, sometimes you have what is called a nominal area. You know the area in beforehand. This is a ship, like the Kigoria case, ship ramming ice, so you know the area if you know the penetration. And it's the same in ice edge. If you know the penetration and width, then you get the area. But these are sort of nominal areas. Then concepts for pressure. It has varied from Kortsavin. He did a lot of measurements on Russia built lots of bridges in Siberia, and they had bridge piers and they had ice. So Kortsavin actually developed the first pressure, to my knowledge, the first pressure thing. And he actually assumed that it is uniform. He didn't say it clearly, but it was implicitly there. Then there are some studies related to rigid indentation on elastic material. So they have a stress concentration at the edges, and it's like that. Then there is a theory by Kurjum and Keisin, two Russians actually, who said that there's a viscose layer between ice and the ship, and then the force is transmitted through this viscose layer, and they divided then using all kinds of material constants. They divided the distribution. So it's fourth root of this kind of quantity, sort of. So essentially, because there's R squared, so it's essentially a square root type of thing, the distribution. Then there were some measurements which suggested that the flexibility of the structure influences that if this is ship's shell structure and if the plate is bending, it reduces the pressure in the middle. Finnish-Swedish ice class rules are based on this idea. This was 1977 first measurements. The present insight actually came, I think, when the tactile sensors were introduced. You were able to measure an array of 100 times 100 points or something like that, and measure the pressure on those. So tactile sensors revolutionized the whole thing. And here then are from Sodhi. This is Joya test in Monbetsu, or close to Monbetsu in northern Japan, in Hokkaido, 1997. And they observed actually that the pressure is like this. Higher indentation speed, it's along a line, but it's like a mountain range along the line. And then lower indentation pressure, it widens this way. And this is the force trace. Here it is very irregular, and here it is quite regular. Important thing is to notice that in lower indentation speeds, the force is much higher, 250 kilonewtons to less than 100 kilonewtons. And if you are a designer, the highest loads are of importance. Anyway, before coming to that, I just say that there have been some explanations for the pressure area relationship. One is the earliest one. One of the earliest one is that the so-called Weibull effect, that there's a higher probability in bigger samples to have a bigger defect. That's the Weibull effect. The other is this non-simultaneous failure, that ice is failing here and there, and then that creates a pressure area relationship, like the DEM calculations, what I showed. And then some people, especially Palmen and Dempsey, have suggested scaling based on fracture mechanics, and they suggested an exponent of minus 0.5 plus beta. And then they state that beta is between 0 and 0.5. It was an interesting episode when I tried to get the value for beta, because in this paper where they had this, they had just a reference for beta to another paper. I went there and it went to another paper, and it actually went a circle. I didn't get beta anywhere. What is that? I'm digressing again. Sorry about that. But it anyway gives you the value of, if this is 0, it is 0.5, and it is 1, then there's no pressure dependency, area dependency. Another idea which came, this is from Hobson's Choice Ice Island. These are from Gagnon's papers. This is actually the result. This is actually one of my students who were there on Hobson's Choice Island. He measured, and this is after the test. This is roughly, this is 0.5 meter, so this is quite large, 1.5 meters. This is crushed area after a test. And you see that there's this kind of dark area, so it shows sort of that the high pressure is on a line. And this is an explanation for this, that there are cracks falling out, because the ice was shaped this cone, very flat cone, but a cone anyway. And then that leaves the center part for the line-like pressure distribution. If you do then a thought experiment, and you have this kind of area, and you use different gauges, different areas, so larger and larger and larger, and measure what is the average pressure. You assume that it's a constant pressure on the line and 0 outside. Well, you get this kind of point area exponent 0.05. And this also, this is a little bit of more calculation for this, that if it is this kind of trapezoidal, you get average pressure of square root of that, but you have also the aspect ratio dependency there. So now we have two competing explanations. One is geometrical, this kind of line-like thing, and the other one is non-simultaneous failure. And we saw also that the failure along the line is non-simultaneous. This is actually a close-up from Joya measurements from Sodhi's, actually his presentation. So it's along the line, it's sort of a mountain range. So these both are there. If you look at then how the pressures are close to each other. So this is actually the pressure sensing plate, and we calculate the correlation of pressure in the middle with different gauges. And this is the 18, so it's, of course, correlation with itself is 1, but it is almost 0 all around. So there's no correlation, and this is 2.5, this is 1 inch times 1 inch. So there's no correlation 1 inch aside, which is surprising if you remember the video, that it was the line looked very continuous. This is from Sodhi's measurements, the same thing, correlation. And this is actually the brittle case, and this is the ductile case, where there's a little bit more correlation. Ductile case is where ice is warm or indentation speed is high. And that has led to this kind of transition speed, the idea that ice is failing brittly in lower temperatures or higher indentation speeds. I have collected results from several experiments here, and then these are the ductile cases where the pressures are not that high, but it's quite much larger, the area. And I have put a line there that what separates these two different cases. It was pointed to me that, well, salinity might influence it, so I actually put a salinity, so there should be actually a third parameter in explaining this mode change, but there are not any results. This is actually the first plot I have seen about this. People have mentioned these values, but not plotted them. Well, I'm running out of time, but anyway, what can we deduce? So them suggest that it is non-simultaneous failure. Then, of course, the geometric distribution creates also an area dependency, and pressure along the line, which explains this geometric thing, contains also non-simultaneous failures. Jury is still out here. Nobody has really analyzed this further, that what is this really? I just mentioned quickly that this causes trouble for us if you apply this pressure area for design. Because in principle, all areas should be checked and corresponding pressures. You have a structure, you start with small area and you vary it somehow, and you calculate the response, and the designing response is the largest value, of course. That is and I have two examples, Finnish-Swedish ice crust rules and the Arctic offshore structure rules. But before that, I just show results of a thought experiment. If this bulk carrier hits a round ice flow, yes, I'm getting out of time. But anyway, in the beginning, it is small, the area, and then it expands the area. And what is the response? Well, if there's no area dependency, response goes up and then suddenly levels off. If there is minus 0.5, the thing is that it goes up, but it reaches a maximum. So there's actually a critical design area for each case, and this is something you have to determine being an engineer. Well, in Finnish-Swedish ice class rules, we use actually the line-light concept and then the square root of area, so exponent is minus 0.5. In the Arctic offshore structures, there are several area definitions. Here are several area definitions which are not that clear to me, or then explanation of nominal area and some design area. But what is it? It's not clear. Then there's a level ice thing. This is the design area, and there's minus 0.5 exponent. This is the pressure equation in ISO, there's thickness there, and this N is negative, so there's a, in a way, pressure area relationship there. Then there are equations which say this one, and then there's another equation, other place, saying this one. And I think that there's still a fourth place where there's pressure area relationship. To confuse the matter, the designer, if you're not very experienced, you're very confused in using ISO 19905. Have so many different possibilities. And problem for design, and this is my last one, is that if the indentation rate, if it is ductile failure, the global pressure, the total force is higher than in brittle case, but the local pressures are lower than in the brittle case. So design is important there. Well, I think I stop here, that just having challenges. I mentioned these challenges already. Physical mechanism, the mode change is important, how to apply the pressure area relationship in design, and how to take the indentation speed into account. Those are the challenges what I see at the moment. Well, thank you.
Any questions, please? We have time for questions. Yeah. Thanks. How much can your work on this pressure be related to the work of the people working on fractures or fractures dynamics and things on solids? Because ice is a solid where you have a crack that is propagating when the ship is advancing. Is by any chance what you try to measure related to some theories on fractures dynamics?
Well, fracture, I mentioned this, that you asked that if fracture mechanics has been applied. Well,
or could be applied, because I imagine it's much more complicated.
Well, it is. Yes, fracture mechanics is important, because it is important if there are cracks running. If the cracks are not running, ice is warm or whatever, then the loads are higher. So this was the mode change actually from brittle to ductile, and that is actually very important.
But also, do you try to understand how the stress is located inside your ice sheet somehow?
On the contact area, yes.
But probably because what we know from fracture is that you really need somehow to know the stress field as a complex structure, at least as a given dependence depending on the tip. So could it somehow be related to what you observe, the fact that you have a high stress variations close to the tips that could somehow play a role in your... I imagine it's not the same scale.
A difficult question. I think that Jukka Tuhkuri here is almost the only one who have done analysis of the cracks running in a contact. I haven't heard anybody really, John Dempsey, yes, have done something, but he has more investigated cracks and fracture toughness and so on. So not much has been done.
Thank you. Thank you. Any other questions? Alberto, any questions online? No questions. Okay. To close, just to confirm that indeed, in many cases, the science is behind engineering. So it could be not right to say behind. It's science following. Is following engineering, and it's good. It's good if you are doing science, like I'm doing applied mathematics, so it should be science, I believe.